Over the past few segments, you saw a number of examples of how equilibrium math, KEQ, can be used to solve an array of problems, cases in acid-base chemistry or precipitation reactions. That's just the tip of the iceberg of what equilibrium math is good for. Over the course of the practice problems that you'll be doing, you'll have more opportunities to see that equilibrium math in practice. Remember, any chemical reaction can have an equilibrium constant expression written for it, and as a result can potentially have an equilibrium constant. Though, as we'll see, some of those may be so large or so small that we don't necessarily have to use equilibrium math every time. Now, we want to address one of the biggest questions that I've been kind of teasing over, well, frankly, weeks at this point. We said we really wanted to understand why a chemical reaction happened, and that Gibbs free energy, delta G, was the tool that finally let us do that. What's more, delta G and our expression for it gave us a way to understand the impact that temperature had on whether a reaction could actually happen or not. However, we said one of the big limitations of that delta G was that it was always happening at standard state previously, or at least standard state concentration and pressure. By comparison, our KEQ that we have been doing quite a bit of math with was giving us a way to finally understand the role that concentration and pressure might play in which way an equilibrium would shift. However, KEQ was very limited in that we could not adjust our temperature. So how can we bring together delta G that lets us account for the impact of temperature with KEQ that lets us account for the impact of concentration? In essence, we knew how to deal with any delta G, variable temperature, and fixed pressure or concentration, while our KEQ was giving us concentration information, but required that we be at equilibrium with delta G equal to 0 and at a fixed temperature. We want to combine these in a way that will let us understand the impact of varying basically everything we can reasonably control about a reaction. We want to understand that impact. So I want you to think back to our Gibbs free energy expression. Our delta H was telling us a lot about things like bonds being broken or formed in some process. And that was all a delightful thing, certainly useful. You might recall things like average bond enthalpy that worked, but the delta S didn't. That is, there was no average bond entropy, because entropy was all about where things were positioned and how many arrangements there could be. Thinking about that idea that arrangements and how many places a particle could go is related to entropy, it might also be a little bit intuitive to think about the fact that the number of ways that something can be arranged are going to be related to concentration. What that means then is that we should expect to see temperature and whatever is going on with our that means that we should expect to see temperature and whatever is going on with concentration showing up together in ultimately the equation that we wind up using. So let's take a look at that equation. This is kind of a big equation, but it's an important one. So I want to take the time to really break down what's going on in it. Well, delta G naught, you might recall that that naught means our standard conditions of 25 degrees C, 1 bar, and 1 molar. So this is effectively the delta G that we were working with last time. That delta G that was a little bit inflexible. Over here, this is something new. That R, that's our ideal gas constant, one we've seen before, and in fact one we dealt with before when we were talking about delta G and delta S math. We also have temperature over here. That's, again, not very surprising. And last but not least, we have the natural log of Q. A quick note here, for some reasons that you'll learn about if you take thermodynamics with Dr. Glaser, that's Chem 342, this does have to be natural log, not log base 10. So when you're doing these calculations, you'll want to double check on your calculator to make sure you're using the correct log. So with that said, we're taking the natural log of Q. Well, what's Q? Q is the reaction quotient. Now, you might be thinking to yourself, reaction quotient? I thought we were trying to look at KEQ. We've spent all this time with KEQs, this way to understand the impact of concentration. Now you're throwing something completely new at me? Well, hold on. This isn't so bad. The reaction quotient is calculated using the same equilibrium constant expression math. The difference between KEQ and the reaction quotient is that a reaction quotient can be calculated for a reaction at any point. In essence, when a system is at equilibrium, the reaction quotient is equal to KEQ. But even when we're not at equilibrium, we can still calculate a reaction quotient. So that suddenly makes this equation incredibly powerful. Because it says the following. For any chemical reaction, if you know it's delta G naught. In essence, if you know the Gibbs free energy and the temperature and concentration of each component, you can determine delta G. That means that we can now determine whether a reaction will be spontaneous for any temperature and any combination of reactants and products in any concentrations or pressures we desire. That is incredibly powerful. I want you to just pause for a moment and think about what it means that we now have an equation that brings these together. What's more, we gain one more piece of information. If we were at equilibrium, delta G would be equal to 0. Let's do this. If these two are true at equilibrium, that means that this expression can now be rearranged to that, also written as such. This is such a powerful expression because it now ties together delta G naught, temperature, and KEQ. It says that if we have an equilibrium constant for a given temperature, and ideally that should be 25 degrees C, we can calculate delta G naught. It also means that if we have delta G naught, we can calculate KEQ for any temperature. So I cautioned you at the start of this chapter that KEQ is temperature dependent, and it is, but now we have a mechanism that we can use to adjust KEQ to function at other temperatures.